So sine of 0 should be 0. Sine of 90 is up to 1. Sine of 180 is back to 0. Sine of 270 is down to negative 1. And sine of 360 is back to 0. So there's sort of the outline of the wave shape. So now let's get some more details in here. Let's start with the first quadrant. So first up, each tick mark is 30 degrees, so 45 would be kind of halfway in between right there. So let's start with sine of 30. All right, well, sine of 30 is going to be a half. So I'll come to there. Sine of 45, that's square root of 2 over 2. So that's about 0.7 roughly. So we'll put that pretty close to that area. And then sine of 60 is going to be square root of 3 over 2. So about 0.87. So we're pretty close to 0.9 there. And then there's a lot of symmetry going on, and that's really the key to the unit circle, is just remembering which values or which quadrant you're in, which values are positive, negative. Once you know these three in the first quadrant, the rest aren't too bad. So it's going to basically be a mirror image. At 120, it's also around 0.87. 45 degrees, we're back to about 0.7, I believe it was. And back to a half when we get to 150 degrees. Back to 0. And then it just kind of goes negative. So negative a half, about negative 0.7, close to negative 0.9. And repeat over here. That's the outline of your wave. I'm going to go ahead and fill those in. We'll just kind of connect the dots pretty closely. All right, so there's a sine wave. All right, and of course you're supposed to do a cosine and tangent. We'll take a look at each one of those too, at least with the calculator, but that's kind of the basic idea. If you can do that, you should be able to get the other two okay. I always like to illustrate the point this way with these waves, because sometimes they're kind of skewed when you see them on a calculator or on Desmos. Any way you really graph them, they get kind of skewed. But they come from the unit circles. So something that I just kind of want you to think about and see. If we start with a circle, and I mean, really we're just kind of tracing what the height is as we go around those different points. Really, all this is a circle kind of cut apart and slid over like that. So I mean, really, it's a very circular looking wave. It may not look like it, but it's really just, it's a circle just kind of split apart. That's really all a sine function is. One of the big adjustments with this, we need to get where we can think of these in radians. So let's cross these degrees out. Let's replace them with radians. So 180 is pi. 360 is 2 pi. Let's kind of just hit the big ones and work our way in. Instead of 90, that would be pi over 2. 270 would be 3 pi over 2. Instead of 45, we'll have pi over 4. Instead of 135, we'll have 3 pi over 4. And 5 pi over 4. And 7 pi over 4. And then 7 pi over 4. Instead of 60 degrees, we'll have pi over 3. Instead of 120, we'll have 2 pi over 3. This would be 3 pi over 3, 4 pi over 3, and 5 pi over 3. And then instead of 30 degrees, it would be pi over 6. 5 pi over 6 over here, 7 pi over 6, and then 11 pi over 6. So make sure that you can think of these all in radians. That's going to be really important, because most of your homework, I believe maybe all of your homework, is going to be in radians and not degrees. Degrees is a good way to kind of get you thinking about how it works. We do need to make that adjustment pretty quick. Just so we can hit the other points on that paper I asked you to do. So there's our sine wave. There were some questions at the bottom of that page, and I kind of want to go through the different graphs and maybe hit those questions for you. So I've got my graph, I've got sine, I've got several things, but this is sine. And something you can do in Desmos, you can actually type in pi and it understands what that is. So I put negative 2 pi to positive 2 pi. And for the step right here, for the intervals, I put pi over 6. And that's how I've got this thing where it's basically, I zoomed out a little bit, but that's why it's counting in pi. By putting that step in pi over 6, that allowed it to count in intervals of pi on the axis. So you can kind of help yourself out with Desmos a little bit there. Cosine, the thing I really want you to notice about that, it's basically sine is just shifted over a little bit. And we'll get into more details throughout the year about why sine and cosine kind of have that relationship. But really, for now, the thing to notice is it's just really shifted a quarter circle down, and it looks the same. So instead of starting at 0, 0, you're going to start at 0, 1. So it's kind of like the whole thing got shifted back. And I'm going to do cosine just to let you kind of notice that. So it's just red is sine, cosine is blue. It's just sine shifted back pi over 2 units, or 90 degrees. All right, now that we've got the preliminary work out of the way, let's look at what can happen to a graph, the things that we can change it with. And it's the same typical things we've seen all year. You can put a number out in front of the function, the sine function here, and that's going to stretch it taller. You can have a number inside with the x. That's going to lead to some changes left and right. It's actually going to lead to one other thing, just because of the way sine works. And then anything you put at the end is a shift up or down. Okay? This is not real typical with waves, because it really doesn't matter how far they're up and down typically, but sometimes the book will throw that in there just to get you practice with it. At this point, I just want to run through what each thing does. I'm going to flip back to Desmos, and let's just kind of see what happens. This is our normal sine wave. I've done everything that I had in that example, A, B, C, and D. So if A is 1, then that's again, this is our normal sine wave. And I said if we change A, that's going to be a vertical stretch. So let's just see if that plays out. And it definitely seems to. If it goes less than 1, it's going to get pretty small. And if it ever becomes 0, it's actually 0 times everything, so it's just a flat horizontal line. I'm going to bump it back to there we go. And if it becomes negative, then it flips every y value over. So it just flips the sine wave upside down. There's a regular sine wave. If I make a negative, it flips upside down. All right, I want to see what happens if I change the b value. All right, let's mess around with b and just see what happens. Now, b is the number times x, so kind of keep that in mind. We won't worry too much about the y right yet. We'll just kind of do it and see what it does. So if b gets bigger, the waves start to get closer together. Now, we're going to have a definition for that term in a few minutes, but for now, the waves are getting closer together. If b gets smaller, the waves start getting further apart. And if it becomes negative, it just flips it upside down. Try to reset that back at 1. All right, c is the number that's added to b times x. So it's inside the parentheses, it's with bx. Now, that's the part that's going to be your horizontal change that you might expect. We're going to have a name for that in a minute, too. And just like usual, it's kind of backwards what you expect. If I go left with the x value or the c value, the graph gets shifted further to the right. And if I go toward the right with the c value, the graph comes to the left. All right, and we'll reset that back to 0. And then finally, d is just going to shift the graph up or down. Again, something we're not going to see very often in this class. Let's try to tie down some definitions to what we were just seeing with these different values. So first up is that a value out front that was stretching it or shrinking the graph vertically. And that's going to be called the amplitude. So the a value, I'll go ahead and just kind of put that in parentheses there. The a value leads to the amplitude. So it's kind of named accordingly. And it's the maximum displacement from the x-axis. So to give you a visual for what all those words mean, this is our typical sine wave. Your amplitude is this displacement, this distance from the x-axis to the peak of the graph. So this would also be a down here. But something that's kind of tricky is that amplitude is always positive. Your a value can be negative, but your amplitude is always positive because it's that displacement, it's that distance from the x-axis. The distance is always positive. The next term is frequency, and that's influenced by the b term. And it's the number of full cycles in a normal 0 to 2 interval. So back to Desmos here. When I change b, and if we just look at a 0 to 2 pi interval, so from here to here, if I make b to, well, b's 1 right now, we have one normal wave, starting at 0, going up, down, and back towards starting. If I go to 2, we should see 2 full waves in that span. So 1, 2. If I go to 3, we should see 3 waves in that span. So 1, 2, 3, and so on. So you get the idea. But that's what's called frequency. So B is frequency. It's the number of waves you have in the normal 0 to 2 pi span. We can actually, with radians, you can go straight to time and seconds. And so then it starts to become a matter of, all right, how many waves do I have in a normal span of time that we can define? And that's where the term frequency really comes in, is how frequent the waves come in. Period is the length of one full cycle. So back to your graph here. If my frequency is 3, then each wave is compressed down. And hopefully it kind of makes sense that each wave would be 1/3 of the normal 2 pi length. So these two go hand in hand. Frequency and period, there's a direct connection between the two. And all you have to do to find period is take 2 pi, which is your normal period, divided by your frequency, your b value, and that tells you how big each cycle is going to be, or how long each cycle is going to be. And again, radians goes directly with time. We can translate these into measuring things out in time for modeling real situations. So period of time is kind of why it's named that way. So again, the way you get the period is you take 2 pi radians and you divide it by the b value, which is your frequency. Finally, is phase shift. That's the distance you shifted right or left. It's not quite as simple as just being the c value. It's a combination of the bx plus c. So I'm just going to put it that way. And I'll get into how we figure that out on the next example, but that's really what it comes down to. It ultimately is a shift left or right, but it's influenced both by b and c. So it's not just as simple as your c is your phase shift value. All right, let's find the period, amplitude, and phase shift, not necessarily in that order. We've got a function here, 3 sine 3x minus pi. To me, amplitude is the easiest thing to find. Remember, amplitude is always positive no matter what your a value is. So think like absolute value of a if you need a formula for it. So amplitude is going to be 3. Now I'm going to go ahead and do all the work and graph these. On the homework for the first night, it says just do these parts and don't graph. And that's really just so you're focusing on the math part now, because the graph kind of has its own added challenges. So just focus on doing the algebra part right now, then we'll build in the graphing too. I think it makes sense to see it all together, so I'll do it all together on this one, but you really just need to do the algebra. So amplitude is going to be 3. Now, period and phase shift. So period goes with frequency. So if we know the frequency, let's just kind of put that in here. Frequency is the b value, so it's 3. The period is going to be 2 pi divided by your frequency, so 2 pi over 3. And once we graph it, I think that becomes more apparent. It takes 2 pi over 3 radians to complete one full cycle. That's the period of time it takes to go through the whole thing. All right, last thing is phase shift. The math's not too bad, but I just like to make sure you understand it. So if you have a normal sine graph, when sine is 0, your y value is 0. That's kind of the beginning point. So what I want to do is figure out, what do I need to do with this stuff to make it equal 0? So we'll take 3x minus pi and set it equal to 0. Again, I'm just trying, this is kind of where you usually begin. I want to see how this thing gets shifted, so I'm going to take where it typically begins, set this stuff equal to it, to see what change would have to be made to this to make it be where you normally start. So 3x is going to equal pi, and then ultimately x is going to be pi over 3. And that's really it. That's your phase shift, is pi over 3 radians. Everything, normally we would start at 0, 0. This will be, the y value will be 0 when pi over 3 gets plugged in for x. So everything gets shifted down pi over 3 radians. And then that's where the graph would normally begin. And you'll see that again in just a second too. So another way to do the period, and also something that'll be important when you go to graph later. I don't really have a name for this. It's just, if this is the starting point, then what I'm getting ready to do is going to be the ending point. That's usually the best way I have to describe it. Well, normally a sine function, if it starts at 0, it ends when you plug in 2 pi, because that's when you get back to 0 and you have a full cycle. It's not the only time you get to 0 in a cycle, but it's when the whole cycle is complete. So same idea, I want to set this stuff equal to 2 pi and figure out what would I have to put in for x to get the same ending point result. So take the stuff that's in here, 3x minus pi, set equal to 2 pi. And ultimately that's going to give us pi for our x value. So again, it's not really any of the 3 things I asked for, but when you go to graph, you start here, you end here. And I was talking about the period and how this is another way to find it. Well, if you start pi over 3 and you end at pi, it leaves 2 pi over 3 radians in between, which was our period. So it's just another way from the start to the end. That's one full cycle. It's another way to find the period. But it's a lot better for graphing, I think. And I like a blank graph to go by here because my amplitude's going to change. The way I label my x-axis is going to change a little bit. So let's see. We're going to start at pi over 3. We're going to end at pi. So I think for now I'm going to start by counting pi over 3. See how that goes. And I might have to add some more stuff in a few minutes, but we'll get there. So for now, I'm just going to do one full cycle, because I just want to kind of get the idea. This thing's going to start at pi over 3, and it's going to end at pi. Really, the only other thing I like to have is if this is kind of the halfway mark, let's get these quarter marks in here. And really, if you think about sine, it goes first quarter, it's up at 1. Midway, it's at 0. Third quarter is at -1. At the end, it's back at 0. So if you kind of hit these quarter marks, that's really all you need to do. There's a few ways to figure out what's halfway between 2 numbers, but I think the most reliable thing, especially as these get more complicated, is just think about the midpoint formula. If you add 2 things together and then divide by 2, that gives you the midpoint. Midpoint's also average. It's the exact same thing. It's an average of 2 points. So that would be 3 pi over 3, which would be pi. And then we're just dividing that by 2 to find what's right in the middle. So ultimately, pi over 2 would be what's in between. If you do the same logic over here, then 2 pi over 3, if you're going to add that to pi, that would have to be 3 pi over 3. And then divided by 2, so 5 pi over 3, and then divide that by 2, so it'll be 5 pi over 6. Now we'll start off with the amplitude, because that's usually the easiest thing to really worry about. Go up to 3, go down to -3. Make sure you do label that. All right, sine graph typically starts at 0, 0. This one got shifted over to pi over 3, 0, but that's where it'll start. And it'll end at pi 0. And we know halfway in between it's back to 0. Now amplitude is 3, so everything gets stretched 3 higher than it normally would. Normally, kind of this first quarter mark, you go up to 1, but we're going to go up to 3. And then at the 3/4 mark, we'd normally be down -1, but we're going to be down to -3. And that's pretty much it. The hardest part, I think, is usually getting these middle points in here, and sometimes getting all the marks for your x-axis. But other than that, it's really just kind of hit the quarter marks, go up, go down, make sure you stretch it far enough. Everything else should be taken care of. It started pi over 3, so that was our phase shift. Period's 2 pi over 3. We can see that if we subtract those beginning and end points. So this one seems to be checking out.